We continue to learn Chapter 5, Orthogonality. Section 1, the scalar product in Rn. Part 2, scalar and vector projection. Orthogonality in Rn. Let x and y be non-zero vectors in either R2 or R3. We would like to write x equals p plus z. So here, p is in the direction of y and z is orthogonal to p. Let u be a unit vector in the direction of y to find alpha such that p equals alpha u is orthogonal to z equals x minus alpha u. So we can see this from this figure. Okay, given you x here and given you vector y here, and we want to write x, decompose x into two parts. One is p, this vector. So it's like the projection of x onto y, and then plus here this vector z, where z equals x minus p. And because p is in this direction y, so p in fact can be written as alpha times u. So we want to know what is alpha, right? So we know alpha equals length of x times cosine theta. And because cosine theta, we can write it as length of x times cosine theta equals, we can write it in this way. See, length of x times length of y times cosine theta divided by length of y. Okay, they are equivalent, of course. And then because this term is just x transpose y. Okay, and so alpha can be computed by x transpose y divided by length of y. Okay, so we can know how to get this alpha. So the scalar projection and the vector projection is defined like this. The scalar alpha is called the scalar projection of x onto vector y. And the vector p equals alpha times u is called the vector projection of x onto y. So one is scalar projection, is a number alpha, and one is called the vector projection, which is a vector along this direction. Okay. So the scalar projection of x onto y, alpha defined by x transpose y divided by the length of y. Okay, and the vector projection of x onto y, p equals alpha times u, which equals x transpose y divided by length of y times u, and u in the direction of y. It is again be computed by y divided by length of y. So immediately we have this formula. So it is x transpose y divided by y transpose y times y. Okay, so this is a vector projection of x onto y. So it's x transpose y, this scalar product, y transpose y. So this scalar product times vector y. Okay. Now we consider this example. The point Q is a point on the line y equals x over 3, that is closest to the point 1, 4. Ask you to determine the coordinates of Q. So like this figure, here we have this line y equals x over 3, and here we have one point, 1, 4. This point is not on this line. And we want to find one point Q on this given line that is nearest, closest to this given point 1, 4. So how to do this? So the vector W equals 3, 1 is a vector in the direction of the line y equals x over 3. Right? And we let v equals 1, 4. So from origin, connecting this point 1, 4. So if Q is the design point, then we know Q transpose is a vector projection of V onto W. So we know Q transpose equals by the vector projection, the formula, it equals V transpose W divided by W transpose W times vector W. So by computation, you can know that this one equals 2.1, 0.7. Okay. So this Q point with coordinates 2.1, 0.7 is the closest point on this line to this given point. Okay, notation. Now, if P1 and P2 are 2 points in three-dimensional space, we will denote the vector from P1 to P2 by this notation. So P1, P2 with an arrow here, upper to P1, P2. Definition, now we give the normal, which is normal. If n is a non-zero vector and P0 is a fixed point, the set of points P such that P0P is orthogonal to n forms a plane path in three-dimensional space that passes through P0. The vector n and the plane path are said to be normal to each other. So a point P with coordinate x, y, z will lie on path if and only if P0, P and n, if you do this scalar product equals 0, if and only if they are normal, right? If n equals ABC, so this is its coordinate vector, and P0 equals x0, y0, z0. This equation can be written in the form of A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. So here n is the normal of this plane, right? And because this plane passes through this point P0, so you have the equation for the plane path in this form. So the normal line, the normal vector n is orthogonal to any vector in this plane path. So we have this equation, A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. You see this example asks you to find the equation of the plane passing through the point 2, minus 1, 3 and normal to the vector n equals 2, 3, 4. So any vector in this plane, you can have this vector, right? So it's x minus 2, y minus 1, so y plus 1, and z minus 3. So this is a vector on this plane, okay? And because this plane is normal to this vector, n equals 2, 3, 4. So you just to the scalar product, they should be 0 here. So the solution is that you just write P0P be any vector on this plane, and then we know that the normal vector and the any vector in this plane, they are orthogonal. Okay. Next example, example 7. Find the distance from the point 2, 0, 0 to the plane x plus 2y plus 2z equals 0. What does this example ask you to do? Okay, so you have a given plane, x plus 2y plus 2z equals 0. You have a point here. This point, if you substitute in this left side of this equation, is 2 plus 0 equals 2, which is not 0. So this point is not on this plane. First, we know this. And then you want to know the distance from this point to the plane. So we can consider in this way, okay? Because n equals 1 to 2 here from the coefficients before x, y, and z, also 1 to 2. This is normal to the plane, and the plane passes through the origin. Let v be this vector 2, 0, 0. The distance of d is the value of the scalar projection of v onto this normal vector n. So the distance d just equals the absolute value of v transpose times n times this normal vector divided by the length of this normal vector. So V transpose n is just 2 times 1 plus 0 times 2 plus 0 times 2, so it's 2. So the length of n is a square root of 1 power 2 plus 2 power 2 plus 2 power 2, so it's 3. So you can get D equals 2 over 3. Now, we consider the length of a cross product. So we know already cosine theta, given you vector x and y, is theta is angle between these two vectors, is cosine theta equals x transpose y divided by length of x, length of y. And it's sine theta, because sine theta equals square root of 1 minus cosine theta power 2. So it equals, we just substitute cosine theta here, and by simple computation, you have this one. Okay, so we have the length of x, length of y times sine theta, okay, equals a square root of length of x power 2, length of y power 2 minus the scalar product of x and y power 2. And you write those vectors, the length and the scalar product in detail, and then immediately by calculation, you will know this one, this square root of this just equals x cross product y is length. So remember this cross product, x cross product y. So how to compute this one? It's just like you write as a determinant, okay? It's first row, for example, you just write any sign, for example, W1, W2, W3, any letter here, and you write the coordinates of this vector x in the second row and the coordinates of this vector y in the third row, right? And then you can have this x cross product y. Its product is obtained by using the cofactor, right? So this is exercise. Ask you to find the equation of the plane that passes through the points P1, P2, P3. So now we know that these are 3 points on this equation, and these 3 points, they are not collinear, so they can determine a unique plane. Then how to get the equation for this plane? You can, for example, you can have P1, P2, right? P1, P2, this vector is on this plane. And also P1, P3, this is a vector on this plane, okay? And if you do the cross product, you will get one vector that is normal to P1, P2, and also P1, P3. This means the vector is normal to the plane, to the whole plane, right? And after you get this normal vector, and you also know this plane passes through one point, given point, and then immediately you can know that using this normal vector, using this given point, you can have its equation for this plane. Okay. Now we consider orthogonality in Rn. In general case, given you 2 vectors, x belong to Rn and y belong to Rn, the Euclidean length of x can be given in this way. Also use the scalar product of x and x, so it's power 1 over 2. So its length equals the square root of x1 power 2 plus x2 power 2 plus t plus xn power 2. And the distance between the vectors also use length of y minus x. So the Cauchy-Schwarz inequality also holds in Rn. That is, you have x transpose y divided by length of x, length of y is no less than minus 1, no more than 1. So this number is between minus 1 and 1. Okay, so before we know this one is cosine theta, right? So of course, cosine theta, this value should be between minus 1 and 1. And the angle between the vectors we also define in this way. also like cosine theta equals x transpose y divided by length of x, length of y, and we know theta is no less than 0, no more than 10. And if you write unit vectors in x and unit vector for y, then cosine theta also can be written as the scalar product of these two unit vectors. So it equals u transpose times v, where u equals x divided by its length, v equals y divided by its length. So the orthogonality in Rn just follows the same way as in R2 and R3. Okay. And given you two vectors x and y in Rn, the vectors x and y are said to be orthogonal if x transpose y equals 0, if the scalar product equals 0, and you can also write as x is orthogonal to y. They are orthogonal. Okay. Vectors and scalar projection are defined in Rn in the same way that were defined in R2. So we can also define the length of x power y, x plus y power 2 equals x plus y transpose times x plus y. So it equals length of x power 2 plus 2 times x transpose y plus length of y power 2. If x and y, they are orthogonal, then we know this scalar product equals 0. So x plus y, the length of x plus y power 2 equals length of x power 2 plus the length of y power 2. If you consider in a triangle, because x and y, they are orthogonal, so they are perpendicular, the two edges are perpendicular, and x plus y is just the other edge, right? So of course we have this one. We are familiar with this result. And this result can called Pythagorean law. Okay. So the Pythagorean theorem, if we set A equals length of x, B equals length of y, C equals length of x plus y, then C power 2 equals A power 2 plus B power 2. So this is a famous Pythagorean theorem. It's just like here. Okay, A equals length of x, B equals length of y, and C equals length of x plus y. And in Chinese, we call it 勾股定理, right? Very famous theorem.